Okay, so the next one is exercise 6.5, where we're always assuming in these exercises that we have a Cartesian closed category. So we assume we have finite products, terminal objects, and exponential objects. Anyway, what we're asked to show is that 1 to the power of a is isomorphic to 1, where 1 is the terminal object, and also a to the power of 1 is isomorphic to a. So the first one's quite easy. An arrow from b to 1 to the power of a by the kind of exponential property is equivalent to an arrow from b times a to 1. And there's only one such arrow, so there can only be one such arrow from b to 1 to the power of a. So that means 1 to the power of a works like a terminal object, okay? Now, the second bit I found very difficult. I did get there in the end, but there's got to be a simpler way, surely, to do it than the way I've done it. Anyway, so I mean, firstly, we want to find the isomorphism between a to the power of 1 and 1. So I claim the isomorphism looks like this. So we have, we want to show the isomorphism between a to the power of 1 and a. Well, we have the an arrow from a to the power of 1 to ones like this, but we do know that there's an arrow from a times 1 to a, which is p1. So if we have this as the exponential adjoint, or transpose is another term for it, that's an arrow at least from a to the power of 1 to a, and I claim that that's an isomorphism. Now the inverse arrow to it, so I call that arrow there f, and then the inverse to it is f to the minus 1, and how that works I think just to make it a bit funnier, I'm using b's instead of a's actually. It's not a big deal. And then the way this goes, we have this sort of unitary isomorphism here, which goes, we keep the b. Oh, excuse me, I'm getting all muddled up. Right, let's start again. We want an arrow, let's say from b to b to the power of 1, and we want to call that f. Well, that's equivalent to an arrow from b times 1 to b that we can call P1, the first projection as a product. And so let's set F is equal to the adjoint or transpose of P1, okay? So that's one way of our isomorphism. The other way we call F to the minus 1, and the way it works, we take our B to the 1, and then we go, well, we keep the B to the 1 there, and we also introduce a terminal object. So this is object, this sort of target of this arrow is B to the 1 times 1. And then if we evaluate, then we get back to B, and the claim is then that the composition of those two red arrows forms the sort of inverse. Okay, so we have to show, basically we want to show that these two things are inverses of each other. Okay, let's just put a bubble around that. So how does this work? Well, we start off with this rather intimidating looking diagram, but it's not as bad as it looks. Okay, so this bottom triangle here, with the red and green arrows, is just the definition of the exponential for P1. And one can see that this kind of top square commutes just by using the orange and green arrows, commutes just by working through the algebra and noticing that like composing this way, there's only a unique arrow for terminal object, so that composition works out to be the composition of this. So that just comes from sort of properties of arrows involving products and stuff. And then these blue, yellow, and purple arrows are just inverses of these unitary isomorphisms, okay? So the first thing is just to have that diagram. The second step, we want to show this equality. So what we're basically showing here is if we go down this orange arrow after this P1 bar, after this P1, that's the same as going along with this green arrow, which is doing P1 bar times 1, where bar is transpose, okay? Now, this is interesting. This is talking about getting an identity for this object here, b to the 1 times 1. And we're interested in that because it's next to b to the power of 1, which we really want an identity for. So we have e after P1 bar times 1 is P1. So if we sort of multiply on the left by 1b comma exclamation mark p, that P1 becomes an identity. And so we have that this is the identity. And then we can just insert, well, here we use identity 1, in fact, which is that P1 bar times 1 is this stuff. So we just replace P1 times 1 with 1b1, comma, exclamation mark, b1, p1 bar, p1. And this is an expression for the identity of b1 times 1. Now, we know that 1b1, comma, exclamation mark b1, which is this this orange arrow in our diagram, we know that's an isomorphism. It's unitary isomorphism, so it has an inverse q1 and unique inverse, in fact. And so if we just write these two, then we see that q1 must be equal to p1 bar p1, 1b, comma, exclamation mark p, comma, e1b. And these two are inverses of each other, so they cancel. So this just becomes p1 bar e1b. So now, finally, we have, so that's an expression for q1. So now, finally, we have, and by the way, all this stuff can be sort of got by thinking about walking round and round on this diagram, because we have these backwards arrows. Anyway, what we finally have is that 1b1 is q1 after 1b1, comma, exclamation mark, b1. And now we substitute in q1, so we get that that's p1 bar e1b, 1b1, comma, exclamation mark, p1. Well, we defined f to be p1 bar, so there it is, and we defined f to the minus 1 to be e1b after 1b1, comma, exclamation mark, b1, which is here. So we have that 1b1 is f after f to the minus 1. So finally, we just have to show that f to the minus 1f is also the identity. But that is not such a problem, because we've got e1b after 1b1, comma, exclamation mark, b1 after p1 bar. Well, since this top square made out of orange and green arrows commutes, this is equal to e1b after p1 bar times 1 after 1b, comma, exclamation mark, b. And this red and green arrow we just used composed just to give p1, and p1 is the inverse to this orange arrow going downwards on the top left. So those two cancel, and we just get 1b. So that's that done. We've got the isomorphism and we've used it. Okay, on to 6.6. Show that if there is an initial object 0, then every object a comma 0 to the a is a subterminator. Show that if a has a global element x, as in if it has a point, then 0 to the power of a is isomorphic to 0. So here's the point. If we have an arrow into 0 to the power of a from an object b, that's equivalent by our exponential property to an arrow from b times a to 0. Now, the only arrows. Now we only have an arrow into, this is theorem 6.3, we only have an arrow into a initial object from an object when that starting object is initial. So there's exactly one arrow. So, I mean, if b times a exists, if there is an arrow from b times a to 0, that implies that b times a is initial, which means there can only be one arrow. So there's going to be either no arrows, or if there's one, there can only be one. So that means that since by that arrow counting, that means these arrows on the bottom, they can either be 1 or 0, which means by this isomorphism, there can only be 1 or 0 arrows from b to 0 to the power of a, which means that 0 to the power of a is a terminator. Now, if there's a point x of a, looks like I haven't actually finished the second part of that. Okay. Right then. Exercise 6.11. We're supposing that this arrow f from b to c is monic, and we want to show that f to the power of a is monic. So this is the diagram that defines f to the power of a. F to the power of a is a unique arrow which makes this square on the right commute. And it also has the property that f to the power of a of g transpose is fg transpose. So suppose f to the power of a of x transpose is equal to f to the power of a of y transpose. Well then, fx transpose is fy transpose, which means fx equals fy. Now, since f is monic, x equals y. So we've now shown that f to a is monic because fa x transpose equals fa y transpose implies x equals y, or equivalently x transpose equals y transpose. Okay, on to the next one. (6.14). So we have these two arrows, little r and little s, coming out of t times a. and we're asked to prove that this top line is equal to this bottom line. Well, we get it just by expanding out, just by moving these inside the brackets and calculating out. Now, the other thing is that when we have an arrow R from T times A to B, and we have an arrow S from T times B to C, then we define S composed over T of R to equal S after P1 comma R. Okay, and that's going to be an arrow from T times A to C. Now we're asked to show that composing over capital T like this is associative. And basically it's quite straightforward. We just sort of work through the algebra. So let's define X to equal T composed over capital T of S. So that's X is equal to T of P1 comma S. And now this thing on the left hand side is X composed over T of R. So that's X P1 comma R, or substituting from here, T P1 comma S P1 comma R, which is T of P1 comma S of P1 comma R. And so we've worked it out. We've worked out this expression on the left. We do similar on the right. So we define Y is equal to S composed over T of R. So Y is SP1 comma R. And then we want to work out T composed over T of Y, which is T of P1 comma Y, which is T of P1 comma S of P1 comma R. And those are equal. Okay, so we're done with that one. And then we're asked to conclude that remember the K thing where we could compose arrows. So we had this sort of funny arrow from a product of exponential objects to another exponential object, and if we fed in arrows there, as in T and X families, etc., and then we did that K, it essentially composed the arrows for us, but it kept in their kind of transpose language. Okay. So it turns out that that kind of feature is associative, and we can prove that using that previous result. So if we can show that it's associative for generalized elements, then it's associative. And this is a diagram that we basically want to show is commute. Okay. So essentially we're going to consider a generalized T elements coming into this object at the top left with bits or components T bar, S bar, and R bar. So we essentially want to show that K triple dot of T bar comma K of S bar comma R bar equals K double dash of K dash of T bar comma S bar of R bar. Okay. So we can basically do this. It's quite straightforward because we can just keep using this feature that we know about how K works, which is that K of S bar comma R bar is S composed over T of R transposed. So that means that this A here, applying it to this K inside, we get that that's equal to K triple dash of T bar comma S composed over T of R transposed. And again, applying that with the K triple dash, we get that this is T composed over T of S composed over T of R. And similarly, all transposed. And similarly, evaluating B in that way gives the other expression all transposed. And we showed that these expressions are equal up here. So that's that done. And since it works for generalized elements, that means this black square commutes in general, which means that these different composition machines, if you like, have associative behavior. Okay. Right then. So next one is 615. I think this is just a load of bookkeeping, basically, in preparation for the next part, where we sort of show that f to the power of a and b to the power of g are actually just special cases of the k. Anyway, so firstly, given an arrow f from b to c, we define ft, or f over t, to be this arrow from t times b to c, which is fp2. So we basically just forget about what's going on with t and just take the second component and apply a little f. Okay. Now, the next thing we're supposed to show is that the transpose of ft is equal to the name of f after exclamation mark t, which is this arrow from t to the terminal object. So remember that the name of f is just fp2 transposed, like so. Actually, we're calling ft fp2 dash, in fact. So that this is our naming convention. fp2 dash is ft, and fp2 transposed is f in quotes, which is the name of f. Okay. So basically, the way we do this, we want to show that the name of f after this arrow into the terminal object is equal to the transpose of f over t, as in is equal to fp2-transpose. So we do that basically by showing that this diagram commutes. So this square commutes here. By the definition of the name of f, because this evaluates to be fp2. Also, this triangle commutes. So we can show that all this stuff in black commutes. And so that means that these top black horizontal arrows compose together, which give f quotes after the arrow into the terminal object, all times 1b. Well, that f quotes after the arrow from the terminal object basically acts in this diagram just like fp2-transpose, or just like ft transpose. So that means they have to be equal, because these transposes that make these kind of exponential diagrams commute are unique. So this is the formal argument if you want to go through it. Okay. So the next part, we want to show that ft composed over t with r is fp2 dash composed over t with is fr, and we get that just by sort of expanding out the definitions. So ft composed over t with r is ft of p1 bar comma r I'm not sure I should be using bar here. I think I might mean just another name for a projection in this case, but anyway, it doesn't matter because we're doing fp2 of this stuff in brackets, which just selects the r, so we get that this is fr as we needed it. Finally, I was calling this also composing over t, but now I'm writing star t instead. But anyway, when we have an arrow, this is just because there's two different ways of composing over t depending on the arrows. And so I wanted to be clear about what the difference is. So I'm using a star here instead. But I mean, basically the idea here is that when we have an arrow G from A dash to A, and we have an arrow R from T times A to B, then R after 1T times G is what we call R star T of G. Okay. Now, what we're asked to show is that R composed over T with GT, with G over T, is equal to this R star TG. So this thing here, R composed over T of G over T, is R composed over T of G P2, which is R of P1 comma G P2, which is R after 1T P1 comma G P2, which is R after 1T times G, which is R star TG. So that's that done. Now we actually use this stuff in this next exercise, 6.16.